Recording, got audio. All right. Who is ready to start talking about magnetism? Believe it or not, it ain't got nothing to do with how attractive females find you. Knows what a magnetic field is. We know what an electric field is, or at least we've got, we understand where electric fields come from. You have a point charge, positive charge or negative charge. Positive charge radiates an electric field out in all directions. Negative charge is the same thing, except the field is all radiating inward towards it. So, what is the equivalent of a magnetic charge? Anybody got a guess? Have any of you ever heard of a magnetic monopole? Nope. Heard of a dipole. But have you ever heard of a magnetic monopole? There's a reason. They don't exist. Now the book kind of fudges on that. It says that we've never observed one. Which is true. We've never observed a magnetic monopole in much the same way we've never observed a leprechaun or a unicorn. Let's see, I don't want to try and write it from memory because I'll mess it up. Maxwell, 626 and 27. Oh, of course, they don't include the one I'm looking for. There are his four equations. Give me a minute here, fellas. I really don't want to write this one down wrong. Nope. Don't tell me I've got the only physics text on the planet that doesn't list his. It doesn't list them. One of the four Maxwell's equations. Basically, that the closed integral of a magnetic field is equal to 0. And And what that means is that there is no such thing as a magnetic monopole. There can't be. If you look at Maxwell's equations concerning the electric field, then they always come down to a charge, a positive or a negative point charge, enclosed inside the surface of integration. But when you integrate over the surface of a closed surface over a magnetic field, it will always equal zero. Which means there can never be, you'll never find the equivalent of a point charge of a magnetic field. You'll never find a north charge or a south charge. If you take a magnet, just a plain old bar magnet, one end is called the north end, or the North Pole, and the other is called the South Pole. Okay, you win. If you cut that magnet into two pieces, then you have two magnets, both with a north and south pole. And if you cut those into pieces, you end up with four magnets, each of which has a north pole and a south pole. So what produces the magnetic field? And what you have to have in order to have a magnetic field is a changing electric field. You need an accelerated electron or electric charge. So when you have an electric current that starts to flow, let me open back up to the textbook. When you have an electric current that starts to flow, an electron spinning round and round, it's going to produce a magnetic field. One side points north, the other side points south. Anytime you have an electric charge moving, even if it's moving in a straight line, it's still going to produce a magnetic field as it goes past. Look at the picture on page 560 of your textbook. It shows an electric wire with a bunch of those little compasses all positioned around it. And even though they're all pointed with north, basically pointing to the top of the page, if you'll look at the little compass needles as it goes around that wire, they all point in a different direction, all of them pointing tangentially to the wire. Because the electric current flowing in that wire is in fact producing a magnetic field that is causing those needles and those compasses to align with it. If you took and drew a picture of that bar magnet, drew the lines of flux of the magnetic field vector lines. Because a magnetic field is a vector field like an electric field. Those lines of flux would do like that. And if you then that Maxwell's equation I was talking about was basically saying if you take any closed surface over that and integrate the magnetic field over that closed surface, everywhere the magnetic field goes in, it's going to have a corresponding magnetic field line leaving that surface. So anywhere it comes in, it's also going to go out. And so that over the entire surface, when you add all of those little pieces of magnetic field together, they're always going to sum to zero. You'll notice if you had a point charge inside that closed surface, that would not be the case. Your electric field would have some net electric field emanating out of that closed surface. If you integrate around if you add it up over the whole surface of all the electric field coming from that point charge. But in the case of the magnetic field, it's like saying anytime you have the negative charge, you're also going to have the positive charge there, so that whatever field comes out is going to turn around and come right back in. Always. Every time. That's how it works with the magnetic field. That's why it said that there is no such thing as a magnetic monopole. There can't be one. If someone ever did come up with one, then they would have to rewrite all of Maxwell's equations. And since Maxwell's equations have been empirically, experimentally confirmed, they're not. We don't call them true because of anything like consensus. They've actually been tested, empirically, experimentally confirmed. They're real. They're law. They're not theory. So, why do we call them the poles of a magnet, north and south? Yeah, it is very much an arbitrary assignment of the polarity of the magnetic field. Magnetic fields have a definite polarity. But why didn't we use plus and minus instead of north and south? Ben Franklin just used plus and minus for the electron and the proton, for the positive and negative charges. What was the first use that we discovered for magnetic fields? Compasses. When ancient voyagers and mariners figured out that if they had a piece of magnet that they could let it spin freely somehow, floating in water or hanging on a string or whatever, that it always pointed in the same direction. No matter where they went with it, it would always point in that one direction, in the same direction as that star that they called the North Star, Polaris. And so the poles became identified as the North Pole and the South Pole. The North Pole of that magnet always points north. The South Pole of that magnet always points south. Because it will always align itself with any other magnetic field it happens to be in the presence of. And the one magnetic field that is always in the presence of is the Earth's own magnetic field. If we did not have a liquid molten core, we would not have a magnetic field around Earth. Is it outside? No. What is the Earth's core made up of? Molten metals. Now, solid metals have lots of free electrons, then molten metals certainly have lots of free electrons. And as the Earth is rotating, all those electrons are spinning round and round and round as the Earth rotates. What are they doing? They're all producing little magnetic fields that all add together to form one big giant magnetic field around the planet. Now, that means that when you take a bar magnet and you suspend it from a string, it will always align itself so that one end points to the north, and we call that the north pole of the magnet. But we also know from experiment that if we take two bar magnets, we have one at the north pole and a south pole, and we bring another one in close, oriented so, with a north and a south pole, these two magnets are going to snap together, and when they do, how are they going to align themselves? This one is going to snap over to this side, this end is going to snap here, and it's going to end up looking like this. So, the north pole of this magnet is going to align itself to the south pole of that magnet. And the north pole of that magnet is going to align itself with the south pole of that magnet. What does that tell you? Opposites attract, yeah. What's that tell you about the Earth? That the Earth's geographic north pole is actually a magnetic south pole. Okay, for those of you who want to pass physics, there be monsters here. The Earth's magnetic field. This is a point of, it was a purely arbitrary choice. Somebody said this is the north pole of this magnet because it always points north. Well, that's because the north pole of the Earth is a magnetic south pole. If you think of the Earth as a giant bar magnet, the geographic north pole is magnetically south. The geographic south pole is magnetically north. And that's why compasses, the north pole of a compass magnet will point towards the north pole of the Earth. So, you ready to learn a right-hand rule of thumb? Clear this up for you because I can tell you this is one that you're going to need to remember. Let's say we've got a coil of wire. There's an electric current flowing in that wire. Back up a minute. I showed you the picture on the front, on the first page of the chapter, with the magnet, the compasses around it. notice that all of the north poles of those compasses are pointing counterclockwise. So that north, 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 north. They're all pointing, so the magnetic field is going in a circle around it, like so. Which way is the current then flowing? Right-hand rule of thumb. Point your fingers in the direction of the magnetic field. They coil around it this way. Your thumb then points in the direction of the current. Okay? If current was flowing in the opposite direction, the magnetic field would then be going in this direction. So, now, let's say we've got this coil, this single loop of wire, and there is somehow magically an electrical current flowing in that wire, in that single loop of wire. And it's flowing in that direction. What does the magnetic field that it produces look like? The magnetic field here is going around it this way. The magnetic field here is going around it this way. All the way around this wire. So, as you get closer to the center and further out, and did I just draw that backwards? Actually, I did. Current is going this way, magnetic field is going this way. So, thumb is that way, zoom. See it? Right. Then your thumb is pointing in the direction of the current.
Like for this case, so like current's going like this. Okay, I was thinking, well, you have to do it with your right hand.
Yep, you got to use your right hand. That's why it's called a right-hand rule of thumb. Don't let that, and don't be discouraged if that's the most confused you've gotten, because there's more than one right-hand rule of thumb when we deal with magnetics.
I was doing it with different hands.
Yeah. Here, it's circling this way. Over here, it's circling this way. The point is, it's always coming out and back in from all sides. So if we drew that just from right on the edge, where that is the coil of wire, but from the edge, then what we have is a magnetic field that looks like this. Everybody see how that works? And of course, it's radially symmetric all the way around. Now, in this case, which is the magnetic north side and which is the magnetic south side? Again, just by convention, the magnetic field lines always point from the magnetic north pole to the magnetic south pole. Okay? That means the Earth has its north pole here, geographic north pole, is actually a magnetic south pole, which means the magnetic field lines of the Earth point from the bottom up. Okay. Anybody have any questions yet? Oh, and for the record, our lab this week is going to be on magnetism. Fortunately, it's a lot easier to actually do magnetic fields and look at them and produce them and measure them directly than it is electric fields. So this one won't be another data analysis lab. We'll actually look at the shapes of some magnetic fields and sketch them using iron filings and little compasses and such. All right, Bill. Let's talk about the forces that magnetic fields produce. And that's going to bring us our second right-hand rule of thumb. First of all, let me make sure you know the notation, standard notation. Magnetic fields are denoted with the capital letter B. Okay, magnetic field would be written as B, a vector B. Yep. And of course, the whole point of magnetic fields is that they exert a force at a distance, but not on just everything. Gravity exerts a force at a distance, but it's a force that is exerted by matter on matter. In the case of magnetism, the magnetic field produces a force on other magnetic fields. Okay? talked about the two bar magnets. If you brought one close to the other one, how they would snap together and on alignment. They would physically exert a force that would accelerate the mass of the magnetic bars. If you have a piece of magnet and you bring it near a piece of ferromagnetic material, it will physically stick and you can feel the force of attraction trying to pull it loose. What is that magnetic field actually exerting a force on? Or what is it actually exerting the force on that magnet that's producing the magnetic field? Because according to Newton's third law, if the magnetic field is exerting a force on something else, then that something else must also be exerting a force on the magnetic field. Which is why when you hold the magnet close to the metal filing cabinet, you can feel it pulling towards the filing cabinet, because while it's exerting a force on the filing cabinet is exerting a force back on it. Now, quick question for you. Trick question for you. How many of you have ever seen these movies like, I don't know, Wanted or something, I think, where they curved their bullets? Or the James Bond thing where they would use strong magnetic fields to curve a bullet? Will a magnet exert a force on a bullet? You take a penny out of your pocket, it's copper alloy. Take a chunk of lead, okay, and now if you've got lead and you've got copper, that's pretty much every bullet in the world. Will a magnet pick up either one of them? Who's got a penny in their pocket? This is okay. Who else wants to make a guess? In point of fact, a strong enough magnetic field can, in fact, exert a force on a bullet if the bullet is moving. Okay? But that is a very complicated something that we're not. It has to do with the fact that the bullet is metal, so when the bullet moves through a magnetic field, the magnetic field will induce an electrical current in the bullet, causing the electrons to start moving in a pattern, which will in turn produce a magnetic field, which will then interact with the magnetic field that's inducing the current. Okay? But there's also other things involved, that the way the electrons flow when they're induced will always be in such a direction as to oppose the magnetic field that induced the current in the first place. And so the point is that you can't do curving bullets with magnetic fields. It's even more true that you can't do it by flipping your wrist. That's just silliness. Right? Who's got a copper penny? Nobody? Okay, well, fortunately, I got a chunk of copper here, and a chunk of aluminum here, and a big old chunk of metal right there. So we see these magnets, they definitely stick to that metal, and they stick to each other. Yeah. Will they stick to copper? Who's guessing? You're guessing. Nope, not to copper, not to aluminum. They won't. They won't stick to copper, they won't stick to aluminum. What will they stick to? Ferromagnetic metals. Basically, did I mess up my deal? Come here, you. Where'd you go? It likes you better than me. Over here. Hello. Did I get the magnets too close to you? Did that mess you up? This way. Come on. You can do it. There you go. Magnets may mess it up. Oh well. Let's see. Magnets will stick to iron. They will stick to cobalt. There's a third one. And I can't remember off the top. Well, steel is iron. It's high carbon iron, or it's an iron alloy. Chromium is added to steel. Chromium is added to iron to make steel. But and then you get the excess oxygen out of it. But it's still basically iron. Point is, there are only like three metals, ferromagnetic metals, that magnets will stick to. Because what is the magnetic field exerting a force on? On the magnetic fields of the ion of the atoms that make up that structure, that make up that metal. They have a strong enough magnetic moment. The individual atoms. What is an atom? It's a positive nucleus with little electrons orbiting around it. And if they orbit in an organized way, they will produce a magnetic moment at the atomic scale. Now, normally, you take a chunk of iron or cobalt or ferromagnetic metal, and all those atoms are oriented in all kind of random directions. So the net magnetic field that the chunk of metal produces it's a wash. It averages out to nothing, to zero. But if you put all of those little tiny atomic scale magnets in the presence of a larger magnetic field, they will all line up with that larger magnetic field. The same way that bar magnet lines up and points to the North Pole. It lines up with the Earth's magnetic field and points north. Well, when all of those little atoms line up and point north, or point to the South Pole of whatever magnet you're holding near to them, then that chunk of metal becomes a magnet. And then is attracted to other magnets. Or if you can reorient all of those atoms and keep them that way permanently, then it becomes what's called a permanent magnet. There are techniques that allow you to do that. But I guess perhaps the most convenient way is with an electrical current. Because, as cool as it is to make a magnet and make it permanent, it's even cooler to be able to make it a magnet at will and then turn it off at will. If you've ever gotten iron filings on an actual magnet, they're hard to get off. That's when it's really convenient to be able to. So if you take a piece of iron and you wrap a wire around it, and then you turn on an electrical current going through that wire, every coil of that wire is going to produce its own little magnetic field, which is going to line up all of the little atoms inside the iron bar or nail or piece of whatever, and turn it into a magnet. But unlike a permanent magnet, if you turn off the electric current to it, then all of those atoms go back to random orientation and it's no longer a magnet. So you can take the big giant electromagnet and set it down on top of the junk car, turn on the switch, and it'll pick the car up, and you can move it over with the crane to the pile of cars for crushing, and you flip the switch, and boom, it just drops the car right where you want it, if you're good at it. And if you're not, then you crush a building. Yeah, as long as it wasn't an important building, right? Well, that's where we're going first. We're going to talk about the force that an electric field exerts. And the first thing we're going to talk about is the force that it exerts on an electric current, since the electric current is what produces a magnetic field. Now, here we've got a wire. And it has a current I flowing through it. All right? Now we have this wire in the presence of a magnetic field. B. Oh, wait a minute. How did I pass over this? Oh, I didn't. Okay. They don't talk about it yet. But we are going to talk about the units of a magnetic field. So, this wire is at an angle theta relative to that magnetic field. Then the force, and what we have to talk about is the force per unit length. So the force exerted on that wire is equal to the current flowing through the wire times the length of the wire that is actually in the magnetic field times the magnetic field sine theta. Now let's talk about what that sine theta means. And it's important to notice here the definition, how theta is defined between the angle, between the wire carrying the current and the magnetic field. When is sine theta, when is this force going to be the maximum force that it can be? When sine theta is equal to 1, which is at 90 degrees. So, if this is your magnetic field, and that's your wire carrying your current, and it's perpendicular, theta equals 90 degrees, then this force is simply equal to, if this is the length, and that's your current, then this force is equal to the current times the length times B. What happens if you take this wire and you turn it so that it's now perfectly parallel? then sine theta becomes 0. And the force exerted on that wire by that, not on the wire, but on the current in the wire, that force then becomes 0. This L right here, that's a lowercase l. That would be this distance, the length of the wire that's exposed to the magnetic field. Because this force is actually force per unit length. Right. Right. So, yeah, this is how you would define force per unit length of wire. But we're not getting there yet. So it's the whatever length, however long of the wire you have exposed to the field. That's how much force is being exerted. Of course, it's maximum when the wire is perpendicular to the magnetic field or when the current is flowing perpendicular to the magnetic field. And it's minimum when the current is flowing parallel to the magnetic field. You'll remember how to do vectors, how to break them down into components, into rectangular components. Look at this. If this is my field B, then what are its components relative to this wire? That is B, and this is theta, then that distance here, from there to there, is B sine theta, that's perpendicular to the wire. And this is B cosine theta. That is parallel to the wire. So the B cosine theta component of the B field vector is producing 0 force, and only the sine component, the perpendicular component, is actually producing the force. The other thing I want to impress upon you is to understand that, what's this wire made out of? Probably made out of copper. Might be made out of aluminum. But it ain't made out of iron. No wire ever was made out of iron. Okay? If you find a piece of wire that was made out of iron, it ain't wire. Okay, unless it's barbed. But that's a different kind of wire. Okay? The point is, this magnetic field is not producing a force on that strip of copper. It's producing this force on the current that's flowing through that piece of copper. Okay? And the force is in what direction? No, the force is always going to be perpendicular to the current. Because it's the perpendicular component of B that is producing the force. It's a vector force. It's a vector quantity. So it's always producing a force perpendicular to the flow of the current. The parallel component of that magnetic field is not producing any force on that electric current. Could be going that way? How would you determine that? That's a really good question, and seriously. What is the direction of the force? Well, it is, but it's also based on that second right-hand rule of thumb. Okay? Here's how you go. You point your fingers in the direction of the current. Then you bend them in the direction of the magnetic field. Whichever way your thumb is pointed, your right thumb, that's the direction of the force. No, in this case, this force would be pointed straight into the wall. Okay? Think of an arrow. If you look at an arrow from one end or the other, if you see the fletching, the feathers, you know it's going away from you. If you see the point, you know it's coming toward you. Okay? If you see the point, duck. But this is the notation for direction into or out of the page or the plane that you're drawing on. Now in this case, you've got current flowing. B field is pointed that way. Your thumb is pointed into the plane. If we turn the current going the other way, then it would be this way. Twist your fingers into the direction of the magnetic field and your thumb points out. If we turn the magnetic field the other way, current's going that way, point your fingers towards the magnetic field, thumb's pointed out. Yeah, in this case, the magnetic field will always produce a force that is perpendicular to the motion of the current and the motion and the direction of the magnetic field. What is that? Mathematically, what am I saying? Remember I told y'all that when we learned about vectors that if you ever get into multiplying vectors, then it matters whether you're doing a dot product, which is a scalar product, or a cross product, which is a vector product. This is a vector product of the vector of the current, cross product with the vector of the magnetic field. A cross product will always be perpendicular to both of the two components that make it up. So, you've got one vector pointing that way, the second vector pointing that way, then their cross product will either be this or this. Anybody have any questions yet? We still haven't talked about the units of the magnetic field, but we'll get there. I think that's the end of class, isn't it? Okay, shoot. Oh, a homework question. Uh-oh. Everybody play Stump the Teacher. Well, let's see. Somebody else may want to know the answer too. Number 39. Capacitors in series and parallel. A 3 microfarad and a 4 microfarad capacitor connected in series. This combination is connected in parallel with a 2 microfarad capacitor. Oh yeah, we can do this one real quick. All right, hold on. Let me get. All right, we've got 2 capacitors in series in parallel with a 3rd capacitor. Where is the supply voltage? Here? And here, so it's like this. Okay. Wait, give me the values of the capacitors. What's this one? 2.0 microfarads. Okay. Series capacitors work exactly like parallel resistors. So, this is the same as, these two is the same as 1 over 3 microfarads plus 1 over 4 microfarads. So, get out of calculators. Three times 10 to the power of minus 6 reciprocal plus 4 times 10 to the power of minus 6 reciprocal equals reciprocal 1, 2, 3, 4, 5, 6, 1.714 microfarads. That's the two in series. They are then in parallel with 2.0 microfarads. Just add the two. So the net capacitance is 3.714 microfarads reduced to however many significant digits we got to work with. Where are we at? 38 now? 38 or 39? Yeah. Yeah, with the voltage, 40 says now if a 21 volts is applied, blah, blah, blah. Find out the charge on each capacitor. And how would you do that? You've got, what is charge? Q is voltage times capacitance, right? Well, you've got 21 volts on 2 times 10 to the minus 6 farads would give you Q on here, which means you've got plus Q, well, actually I guess it would be plus Q down here and minus Q up here. And here you have 1.714 microfarads from here to here. Times that same 21 volts, which would give you the Q across here. Okay, which means plus Q here, minus Q here, plus Q here, minus Q there, or Q2, where that's Q1. Right? Any questions about this? Anybody got homework to turn in?